The integral that we have here is very similar to the one we did earlier, just a slightly more complex denominator. So if necessary, refresh your memory on the other integral and then pause the video and try and tackle this extended version of it. Okay, let's go. First thing we need to figure out is our function f of z, which we will integrate. And just as before, we will use a trick of having a complex exponential here, exponential j by z, because if we evaluate this thing on the real axis and then take the imaginary part, we will end up with sine of pi x. So that's the same trick as we used before, and that way we don't have to worry about needing to split up in two different contributions with two different contours because of Jordan's lemma. The denominator, no big surprise there, z minus 1, z minus 2. And again, we're going to evaluate this on the real axis in the end and take the imaginary part in order to recover the integral that we're interested in, this thing over here. Okay, that's one thing taken care of. The second thing we need to worry about is the contour. Now, obviously, we need to include somehow the real axis because, okay, this is what we're after. And then we need to close that. And let's close that in the upper half plane. Later on, we'll verify that this is indeed the correct choice for this case. But we need to worry about these three singularities that we have here. So we have one at the origin, 1 and 2. So let's neatly sidestep those singularities and have a contour that looks like this. And we'll take the limit of this thing going towards infinity and of these small radii going towards 0. Good. Let's focus on the contribution from this semicircle here in the upper half plane. For that, we have Jordan's lemma, or Jordan, I should probably say, because the guy was French. So first of all, let's have a look at whether or not we're in the right half plane. Well, looking at the exponent here and the coefficient, that's a positive number, so we know this should be the upper half plane. So that's good. Check. The next thing we need to verify is the limits of the other factor if we go towards infinity. So we need to worry about the limit at infinity of 1 over z minus 1, z minus 2. And this indeed will become 0 because here we have a power of z to the power of 3, and this is just a constant. So both conditions for Jordan's lemma are fulfilled, so we can forget about this contribution here. For the three little circles, we have the small limit theorem that we need to apply. And for that, we need to calculate three limits. So let's do that now. So first of all, we have the limit at 0 of our function, exponential j by z, divided by z minus 1, z minus 2. And let's not forget z minus the origin, of course. And then we evaluate that at the origin. And as expected, we have some cancellation going on. So if we evaluate that, we have exponential to the power of 0. That's going to be 1. And then for the denominator, minus 1 times minus 2, that's just going to be 2. So the first limit is 1/2. Right, 1 down, 2 to go. Next up, limit at 1 of exponential j by z. And I'm going to immediately get rid of z minus 1, both in the numerator and the denominator. So we end up with z minus 2 here. Exponential j pi, that's going to be minus 1, of course. And then we have 1 times minus 1, so that is 1. And then finally, we have the limit at the point 2, exponential j by z, divided by z minus 1. So exponential 2 pi j, that's going to give us 1. And then here we have 2 and 1. So this is also 1/2. Good. If you want, you can pause here and reassemble everything in the correct formula. So let's take all of our puzzle pieces and bring them together. So if we take all of the limits, we end up with, on the real axis, an integral from -infinity to +infinity of exponential j pi x dx divided by x minus 1 and x minus 2. And strictly speaking, I should have a principal value here, because this complex exponential also includes a cosine part which diverges. Okay, that's a small technicality. And then we obviously still have the contributions from these three little circles, of which we calculated the relevant limits here. So we have that this is going to be equal to j times pi. Well, actually not pi, but rather minus pi, because we traverse it in this direction. So this gives us minus pi as an angle. And then we have the limits. So let's just add the three limits together. So we have half, 1, and then half. So all of that is equal to 0, because we have no singularities inside the contour. We were very careful to close them in the upper half plane so that we don't need to worry about calculating residues. So that's very efficient. And if we now take the imaginary part of this whole expression, then we end up with an integral from -infinity to +infinity of sine pi x dx divided by x minus 1, x minus 2, x minus 2, bringing that to the other side and taking the imaginary contribution, that imaginary part. This becomes a 2. So finally, the end result for this integral is a very elegant 2 pi.